Hello, this is Bill Mook. Thank you for showing up here and listening to my lecture on a sustainable industrial future. Um, my goal is to show that we can increase our standard of living worldwide for all people and do so in a sustainable way. Um, Also, if America elects to lead the way, uh, we can expect that American leadership in the world can be restored, not through military might or economic cleverness, but by supplying fundamental improvements in the way we live on this planet. The first innovation that is sort of the easiest, I've organized these in terms of complexity and in terms of difficulty, with the simplest being first. Um, Communications. We have the technical means to dramatically improve our communications. And this entails creating a global wireless hotspot. This is an image taken from Teledesic's business plan. This is their original plan of 880 satellites in polar orbit around the Earth, satellites that communicated with each other and with the ground. Um, they Teledesic bowed to powers that be at the time that they introduced their technology, but this technology really could go further. Rather than require an intermediary ground station, we could build satellites that communicate directly with portable systems on the ground. They use a optical backbone, an open optical system to communicate from satellite to satellite, and then a phased array antenna that paints a stationary array of cells on the ground, virtual cells, using GPS signals to locate the cells. That way, a very simple IEEE 803B chipset, modified slightly for time delays, would be able to communicate with the network. And that's the technical means by which we would put together such a system. With such a system, we would deliver internet, of course, broadband internet throughout the planet. Uh, Through the internet, we could provide traditional services, radio, television, um, telephone services at very low cost to everyone. We also could provide financial services. Microbanking would be a growth industry delivered by internet. eBay would expand dramatically, those types of services. The basic internet service worldwide would generate tens of billions of dollars a year. Banking, insurance, mediation services, all sorts of things like that in regions that are less stable than Europe and United States and Japan and in parts of Asia are would benefit greatly from these services, and it would be a driver. Those would be in the hundreds of billions of dollars a year. Then, with sufficient bandwidth, and this would have 50 billion broadband channels the way I've designed it, would be advanced systems, which would use biometric protocols, signaling protocols, as well as a virtual reality transfer protocol on IP to deliver virtual tourism, where you would interact with a sensorium, a sensory system that would reproduce a virtual reality of being somewhere. A lady in Tokyo visiting Paris by virtual reality. Uh, then, of course, you could have a full, this is like one-way communication. You could also have full duplex communication with very simple robotics. One of the problems with robotics is we don't really understand how to program a robot to function in an environment efficiently. We can program a robot to do very simple things. More complex things are still beyond us. It won't forever be beyond us, but this is something we can do today. With the communication system just described, a person can live anywhere and work anywhere else. And this will create vast new wealth. Today, the planet Earth generates about $70 trillion. There's about 3.1 billion people at work. If those folks were able to work anywhere and live anywhere, the number of employed people would increase dramatically and the wealth would multiply dramatically. The same thing happened with the introduction of the railroad and the introduction of the automobile in the United States and Europe in the end of the 19th century. We could reproduce many of the benefits of automotive travel through a telerobotic system and dramatically increase opportunities for work and also increase the value of that work. Okay, so that's the first step, and that could be done, that could be initiated immediately and carried out within a 3 to 5 year period to dramatically transform life on Earth and to improve things dramatically on Earth. The next issue is energy. Of course, energy is a huge issue because there are two aspects to energy. One is our current system of primary fuels using coal, oil, and natural gas produce carbon dioxide, which at the quantities we're using them right now exceeds the ability of planet Earth to absorb them. So they build up, CO2 builds up in the atmosphere, which modifies our temperatures. The other thing is that's happening is that these supplies are running out. Natural gas and oil are in short supply. Coal, not so much, but coal is difficult to work with, which is why natural gas and oil became so popular. The way to solve the problem is with very low cost terrestrial solar. People talk about technology without talking about cost, really aren't addressing the issue. We must lower the cost of energy to maintain an industrial society. If the cost of energy rises, its use diminishes, and our industrial world diminishes as well, and the wealth we can create diminishes as well. Yes, we can improve efficiency, but thermodynamically we can't get over 100% efficient. And right now we're over 50% efficient in many of our operations. So that improvements in efficiency will only take us through one doubling period. And at a 7% growth rate, that's 10 years. Continuing doubling means that we must increase our energy use, which means that we must decrease the cost of energy. And this requires that we have some sort of technology that can be less expensive than present-day coal, oil, and natural gas. This gives us a target. And the only technology that I see that's broadly available and available near term is what's known as concentrated photovoltaics. We concentrate the sunlight to a tiny point, and at that point put a very low-cost photovoltaic device. Some people say we can boil water or produce a steam engine or do a Stirling engine, which is correct, but the cost per watt is the driving factor, and the cost per watt of a mechanical system, of a thermal engine like that, is very high. The cost per watt of a photovoltaic device is not so high. But the target price and the cost of photovoltaics require us to operate at 5,000 times solar intensity. And that means that that's a target. And since the optical limit of concentration on Earth is about 40,000 times, concentration, this is well within reach. We also need to reduce the cost of optics. The cost of the photovoltaic material is high. The cost of the optics must be low. if we're going to reduce our costs as well. And we have to come up with innovative ways to manage heat once we concentrate to this level. And finally, we have to come up with innovative ways to track the sun. As you concentrate sunlight, the field of view of the optical system is reduced. There are holographic means available to provide a solid-state tracking mechanism requiring no moving parts. So what we have here is a solar panel that costs pennies per watt for total system and uses very little photovoltaic material and some sort of very low-cost optical system, and can handle heating levels that are produced, and doesn't need to track the sun, so you can just put them on the ground without any special installation. Then finally, new approach to intertie and storage. Photovoltaic devices produce DC power when the sun shines, and any generator must match its load. If you produce too much power for a load, you have problems. If you produce too little power for a load, you again have problems. So load and generator must match. The problem with any solar system is that as the lighting conditions vary through the day, your load must match your generation. If you're using solar 100% of your energy, which is our ultimate goal, you must have some sort of way to tie this into an existing system and store that energy for when it's needed. And so this is another, and this all must be done for pennies per watt. So that leaves batteries out as we know them. One thing that is possible is a very low-cost alkaline-based electrolysis system that makes hydrogen and oxygen from water using DC electricity from the sun, and then stores the hydrogen in underground formations where natural gas used to be, and then retrieve that hydrogen as needed and distribute it through a pipeline network. That is one approach that appears very feasible and achieves our price points. Okay, so now that we've solved our energy problems and our primary energy problem and our communications problem, then how do we get this energy around? And this all goes into transport media. There is an order of battle in once you have a new primary source of introducing it to the market in a way that is not disruptive and also sustains powerful economic growth while doing it. And the first step is alkanes. Alkanes is a chemical term for the stuff that we burn now. We burn carbon, we burn hydrocarbons, we burn methane, that's an alkane. We burn octane, that's an alkane. We burn nonane, that's an alkane, that's jet fuel. So, you know, butane, propane, these are all alkanes. They're made of combinations of hydrogen and carbon. And I just described a way to use low-cost solar power to make low-cost hydrogen. We could jump directly to a hydrogen economy, but it's most efficient if we're serious about reducing CO2 emissions to continue with direct hydrogenation of coal. Basically, we attack stationary hydrogen use. We build a pipeline network from our solar panels and our electrolysis units, a pipeline network along rail lines and road lines and existing pipelines in parallel to the 4,400 coal-fired power plants in the world. We use 870 million tons of hydrogen to replace 5.5 billion tons of coal and eliminate 20 billion tons of CO2 emissions. That cuts our carbon emissions in half and gets us to where we need to be in order to sustain life on Earth. We also use additional hydrogen, an additional 600 million tons of hydrogen, to combine with half the coal that we're not burning anymore in the coal-fired power plants to make about 18.7 billion barrels of syncrude. And then we add that syncrude to 14 billion barrels of crude oil. So what we're doing is we're cutting the conventional output, and then we also use hydrogen. We mix hydrogen gas with natural gas, half and half, on an energy basis, and send that out, and reduce carbon by half there. So what we're doing is we're cutting our carbon use in half. We're still operating coal industry, natural gas industry, and oil industry at half capacity, but we're supplementing it innovatively with hydrogen in a way that allows us to increase our oil use. Having a slight increase in oil at this time at a low price actually helps moderate energy prices. So this is the first step. And why do we do this? Because this system that I just described is 25% the size of a full-blown system where we're using hydrogen for everything, but it's 50% reduction. So it's a way to invest our money and get double the effect on our CO2 production by using the existing system. And it also maintains long-term value of the energy infrastructure and builds significant new hydrogen infrastructure. So what happens is that we're put in a position where we're cutting our output of alkanes in half from conventional sources, supplementing them with synthetic sources, and we're putting a very strong hydrogen network in place. That pipeline network to the 4,400 stationary power plants will be the starting point of a hydrogen economy. And we only have to build 25% of the system that we ultimately need in order to get half of our CO2 reduction. Then what we do is we cut the other half out over the next 20 years. Actually, since the planet Earth can absorb carbon dioxide at a certain rate, reducing it by 50% quickly gets us out of danger more quickly than building the much larger system. So this is the battle plan for once we have our solution for energy, this is the way to make use of it. Once we have the system in place, then we go from alkanes to protons. That is, we decrease and do not grow our carbon usage. We increase all of our energy increases through direct hydrogen. This is the Cadillac Provoque, which is the hydrogen-powered Cadillac. And this is the future. The future is hydrogen, and those are protons. Up to a certain point, once we get to about 75,000 square miles of land covered with solar panels, we then should think about moving from protons to photons, collecting energy in space where there's never any night, never any cloud, and then beaming that energy back to Earth in the form of infrared laser beams. Many people have heard the idea of beaming microwaves to large antenna farms on Earth. There's a lot of stuff wrong with that. Using infrared is the same. We have an infrared window in the atmosphere, same as we have a microwave window. And infrared is what the sun radiates much of its heat in the form of. So what we're talking about here is basically replacing the sun, putting a 1,000 nanometer wavelength free electron infrared laser, very high efficiency, operated by solar cells in space. We can beam energy to Earth. We can beam energy to Earth in very tight beams, not large beams. Also, infrared energy is already penetrating the atmosphere in large quantities every day. So this infrared energy is not going to harm the environment in any way. Thirdly, at a 1,000 nanometer wavelength, it's very close to the band gap energy of silicon. So it's very efficient. When it's absorbed by silicon, over 98% of the energy shows up as electricity. So there's very little loss. Finally, holographic techniques, the same techniques that the creators of Star Wars or the Strategic Defense Initiative proposed, can be used to produce multiple beams to safely and reliably target receivers on the ground and no matter what happens with the satellite, what happens with the atmosphere, those beams will not move. The technique uses what's called conjugate optics and a system of pilot beam. That is, basically we send a reference beam to the satellite sees the reference beam and produces what's called a conjugate beam in response, which follows the pilot beam back to the receiver. And when the receiver no longer wants energy, you turn off the pilot beam, and then the power beam stops as well. Anything that intercepts the beam, a bird flying through it or an airplane, it's the same energy as sunlight, but it flying through the beam interrupts the pilot beam and shuts the power down for the duration of the object being in the beam. So it's sort of like a fuse system as well. It's a very, very elegant solution to our energy problems, and it's one that really needs to be talked about more. And it deserves its own PowerPoint presentation, which I may do in the near future. But this is the way we go. We replace our existing energy use with hydrogen augmented alkanes. We then do growth through expansion of a hydrogen economy to about 3 times our current energy consumption levels. And then beyond that, we beam energy to receivers on Earth from satellites, and then beam energy directly to receivers, either mobile, on the ground, or stationary. We start with the stationary. We basically convert our solar panels that we've installed for the hydrogen economy. We augment that with beams from space, and once we get good at that and reach our price points, then we start beaming to individual receivers on the ground. And this could be millions of receivers, and these things can be moving at ballistic speeds and still be adequately tracked with this laser system. Again, this whole thing, tracking system, deserves its own PowerPoint presentation. But that technology, which is 1980 technology, does produce fabulous results and provides a clean, safe, reliable energy for our future. Okay, so we've solved the energy problem. We've solved the communication problem and the labor problem. What about raw materials? Well, we need new resources for sustainable growth. One of the things that we can do with by reducing coal consumption, if we're not burning coal, if we're not burning natural gas, if we're not burning oil, we can use those as carbon feedstocks to make plastics. And this is an immediate solution for improved resources for life on Earth. This is the 1960s Monsanto plastic house at Disney World, Disneyland. And this is something that has not really been done on a large scale. But it is a way for coal, oil, and gas producers to produce something of lasting value. That is, people say, well, coal and oil and all that it's not renewable. That's true. But it's being used at a far less rate and at a far higher value. We have the capacity, and we have lots of people who are starving and poor. And so those folks, and everyone actually, can benefit greatly that instead of burning a gallon of gasoline after a few minutes of use, we can make something out of a gallon of gasoline. Instead of a gallon of gasoline, we can make a beam or a piece of furniture, an article of clothing that would last for years. That is a much more efficient use of these carbon, and it doesn't produce CO2 emissions at the end of the day. The other thing we can do with lower cost energy and more abundant energy available from the sun, we can use ceramics in innovative ways. This was again talked about in the 60s, but was sort of abandoned as the cost of energy rose because we have a substitution to make. If we have if we have nuclear power that's too cheap to meter, then we can do all sorts of wonderful things with rocks and make fabulous ceramics. This is a glass house built by the Johnson family, Johnson and Johnson fame, to sort of promote this concept back in the 60s, 50s and 60s. A fabulous house made of very innovative materials that the energy crisis of the 70s knocked out of possibility. What we're talking about when we solve our energy problem in a way that addresses the fundamental cost of energy, making it lower, making it more available, we reintroduce some of these futuristic concepts of the 1950s and 60s, and we open up the possibility for a better future for everybody. So in addition to using our carbon resources more efficiently in the form of plastics, we also use ceramics in innovative ways that is not possible to do today because of energy costs. And then finally, there are some things that we need specific metals for in specific amounts. Solid state devices need very rare earths. There are rare materials needed in the construction of jet engines and rocket engines and things like that. And these special materials cannot be substituted easily with ceramics or plastics. So we need new sources for those if we're going to use them in larger quantities. And those sources come from the ocean. We know how to navigate and operate on the ocean floor. We've been doing it for years. It's been a staple of the Cold War. Nuclear-based submarines, nuclear submarines based in the ocean that carry nuclear missiles for mutual assured destruction. We've spent trillions of dollars doing this sort of stuff. We know how to do it. We just don't talk about it. And it's not part of the commercial sector. The thing is it could be. This is another very easy thing that we could do by changing our paradigm. And we can open the oceans to development. And 2/3 of the earth is underwater. And there are materials under earth just like there are materials on land. And we know how to search for them. We know how to find them. We know how to develop them. It's just not been done commercially. And it needs to be done commercially. We have shortages. We have needs. If we can avoid war by creating new materials, that's a much better use of our time and attention than preparing for war because there aren't enough materials. It's just that simple. And we have the technology to open up the oceans. Another thing that sort of puts this in the realm of science fiction, but it isn't, it seems to, is off-world resources. There's much talk about deflecting asteroids. This is something that was studied secretly in the 50s and became subject of an MIT paper, a Massachusetts Institute of Technology paper in the early 60s. Some grad students did it. But basically, you heat up a section of an asteroid very quickly, and you get a vapor explosion, and that puff of material coming off of the asteroid acts like a little rocket. And you do that thousands of times, and you can navigate an asteroid. You can take an asteroid and move it anywhere you like. Of course, in movies and in popular idea, especially after the knowledge that the asteroids destroyed the dinosaurs, the idea came that we could deflect an asteroid if it happened to be heading toward Earth. That's a very good thing to be able to do, but it's also a very rarely useful thing. A more useful thing is to grab a rich asteroid and bring it into orbit around the Earth, and then use telerobotics and other techniques to develop that asteroid in space. So we use space-based power, telerobotics, and this asteroid capture technique to bring rich materials into orbit around the Earth and then mine the materials. And then just like you have a JDAM that can fly down an elevator shaft after being dropped from an airplane several miles away, you can drop refined materials anywhere on Earth from an orbiting asteroid and launched by a solar railgun. So those sorts of things are very easy to do and well within our capability of doing, and something we should plan on doing in a very near future, and make it part of mainstream business. So with these approaches, we really don't have raw material shortages. Um, Food and water. Food, fiber, and water, really, because we use wood and paper. Um, this is the next big problem. Um, I mentioned earlier that of the 6.8 billion people on Earth, 3.1 billion are employed. We have a 30% unemployment rate worldwide. And in addition, we have about a billion farmers. And most of those farmers are subsistence farmers. We have about 900 million people that are not well fed, and 18 million people a year die of starvation. Much of the turmoil in the world today, much of the abortions, much of the problems that we have are because people face starvation, they know of others who face starvation, or they have faced starvation in the past. And this is a huge motivator. And ignorant people think that without this threat of starvation, the world wouldn't be viable. And really, they need to know that the world is being destroyed by our total lack of progress in this area. If we use scientific farming practices on the land that the billion subsistence farmers in the world were using to grow food, we would have an overabundance of food. We'd have a huge abundance, huge variety, great quality, and great variety. So what we're talking about is the big problem, though, is those 1 billion farmers, we only need about 40 million of them using scientific methods of production of food, 40 million of them to get this increase. So where do the billion go? Where do the bulk of those billion go? And this actually reproduces in the modern age what happened in America and Europe during the industrial age. McCormick invented a reaper that made farmhands obsolete in the middle of the 19th century. And all those farmhands came to the cities, and they were known as surplus population. Charles Dickens talked about it in his novels. Henry Ford had the answer to that: mass production. Make things in such large quantities so efficiently that the people making them could afford them. And that was a huge innovation. Automobiles in the United States are considered commonplace. Everybody has one. In Henry Ford's time, they were considered playthings for the rich. A wealthy man had a horse. A super rich person had a mechanical device that replaced a horse. Henry Ford had the mad idea that everybody should have an automobile. That way, everybody would be put to work, and they would consume the output that they produced. It was a very simple idea. The only thing that was required is that the efficiency of production increase enough to do that. And that's what he did. And it worked. And it created the American middle class and the American way of life. What we're talking about is reproducing this on a massive scale, on a global scale. This is what America can give the world. This is what America can use to maintain its leadership in the world. By taking this vision, using advanced robotics, telerobotics, and other technologies to put the billion unemployed to work and the billion subsistence farmers to work at very highly productive and satisfying jobs, and retain 40, 50 million well-trained scientific farmers to increase the food supply of this planet so that we really do not have a food shortage. The other thing we can do is low-cost greenhouse. Basically, plastic film inflated by air. This allows us to reduce our impact on planet Earth, to reduce our impact of farming practices, and to increase the productivity of land. And low-cost desalination. The food supply is really a water supply problem. And with low-cost energy, multi-stage flash evaporators powered by the low-cost solar energy is the way to go. We basically get to 30 cents a kiloliter for water and less, then we're golden. We're basically at the price of river water, and with scientific farming practices, we have low-cost food. And that's basically what we're talking about. Finally, I wanted to re-emphasize telerobotic labor. Farm hands can report to work from anywhere on Earth to anywhere else on Earth by robotics, using virtual reality and teleoperation. This is, with this technique, combination of techniques, we really have no food shortages. We have no reason to have food shortages, whatever. And finally, off-world farms. There are thinkers back in the 60s and 70s, even back as far as the 20s, that talked about building large pressure vessels in space. We capture an asteroid, put it in orbit around the Earth, put factories, solar-powered factories operated by teleoperated robots on orbit. We can build large pressure vessels in large quantity in space at very low cost. And we can actually create those pressure vessels to grow food and fiber forests and farms on orbit and deliver food and wood to anybody anywhere on Earth as easily as we can deliver a JDAM to any point on Earth at far less cost, of course. Basically, we build these things on orbit from materials we bring to orbit from the asteroids belt, and then we use rail guns, solar powered, to eject things into a descent trajectory that then flies to a specific point on the ground in response to an order. Again, this is an achievable goal. This is only done at a certain price point, that is, when the price gets to a certain level. But this is the target of research. This is the target of where we should be going. And the goal is to remove all of our farming activity and forestry activity off of the surface of the Earth into orbit, so that the only thing we have on Earth is a residential park and a nature preserve with our industry in orbit. Transport. None of these things are possible without a sufficiently advanced transport system. And also, transport is one of the major users of energy. So this is important to think about. I'm proposing that all transport be affected by ballistic techniques, low-cost ballistic transport. What we're talking about is tossing things. And tossing things is actually, tossing a thing from point to point is actually the lowest energy way to move things around. There are three ways that we can move things. We can toss them, we can roll them if they're round, or we can slide them. And here's a picture of something being tossed, something being rolled, and something being slid. It is very low energy it doesn't take a whole lot of energy to drive a golf ball a long, long way. A bowling ball takes more energy because it has this rolling friction. Sliding is the most energy wasteful of all. Climbing up a child on a slide has to raise himself up and add energy to himself in order to slide down the sliding board. So it's important to know that tossing is the most efficient way to move something. The reason we don't do it more frequently is its cost, and that has to do with two factors, lift and power. It takes a lot of power to energy applied very quickly to toss something. Um, it may not take a lot of energy to drive a golf ball a long way, but it certainly takes a lot of power. The smack of the golf club against the ball transfers a lot of energy very, very quickly. So it's a very high power event. Moderate power is rolling. Um, it takes an in-between amount of power between sliding and tossing to roll something down a road. But you need roads and you need wheels and all that, and that's a huge overhead for the rolling. The sliding, as the supertanker shows, is a very low power system. It doesn't take a whole lot of power to move a lot of weight, even though it takes more energy per mile or per kilometer. So the thing is that this is why. It costs money to deliver power. Engines are rated in dollars per watt or dollars per horsepower. And so it takes a lot more money to deliver more power than it does to deliver low power. The other thing is the cost of lift. You have to lift whatever it is that you're moving. If you're floating it on the ocean or carrying it on wings, it's a very low-cost system to do that. Wheels are a little bit more expensive. They're complicated. They need a bearing. They have to be guided. It's a moderate cost device. Rocket engines are very high cost. So to toss something with a rocket is very, very costly. And made so in part because the United States currently has in place missile proliferation controls. We don't want rocket engines to be cheap. We don't want rockets to be cheap. We want to keep these rockets and rocket technology out of the public arena, out of commercial use for security reasons. This is a mistake in the modern world. First off, we're not more secure. Nations like North Korea, nations like Libya have rockets. Doesn't make us secure to isolate the business community from the use of these rockets. So the thing is that we must weigh our security needs with the very real benefit of low-cost rockets, and make this technology more widely available. Change that policy so that commercial entities have access to critical technology. So the thing that I'm saying is that rockets are great if we can get their cost down, and there are a couple of ways we can do that. The first is we can use reusable rockets. We have right now a missile control paradigm in place that restricts knowledge, and the idea of a reusable rocket is something that has been on the drawing board since von Braun designed the Apollo moonship, but has not made it into public discourse or commercial reality. The most recent attempt was the McDonnell Douglas DCX reusable rocket. The rocket took off, flew around, and landed. It's a very simple concept, and it's something that can be done, but it's not something that has been promoted. The other thing is the development of what I call a commodity rocket, a MIMS rocket, a micro-electromechanical system, mass-produced rocket. These rockets are made the same way that integrated circuits are made. Very complex integrated circuits can be made. The same technology that allows us to make a circuit also allows us to make mechanisms that are very, very tiny. We make circuits the size of viruses. We also can make ratchets and gears and all sorts of mechanisms the size of viruses. This allows us to make arrays of rockets that are very, very tiny. Here's a TRW microthruster array, smaller than a penny. Here are some microthrusters that are smaller than a match head. These systems can be made to form a surface. just like high-definition TV made with plasma has many, many points of glowing plasma that are very finely controlled to paint pictures in real time on, with millions of elements, we can create millions of rockets across a propulsive surface to create thrust effects on that surface. And this gives us the ability to create a highly controllable system. Then finally, instead of using existing rocket propellants, we can use air or some other simple gas and laser energy to produce rocket effects. Here is Lick Mirabeau's laser light craft uses this technique, uses air and laser energy to produce thrust. And here he uses a laser beam developed for the Strategic Defense Initiative again to target his laser light craft, but instead of destroying the craft, he propels it and flies about 40 feet in the air. It's a good proof of concept, and it's something that we know how to do and can be developed much more than it is at present and radically transform our approach to transportation. Here's another light craft approach using two laser beams of different frequencies. One is a metering pulse, which evaporates a plastic, and then another is a detonation pulse, which detonates the plastic, using a technique developed by Jordan Kerr at the Lawrence Livermore National Lab. Again, this is something that has been talked about for over 30 years and has been tried in various forms. What happens, we talked about power satellites in space beaming infrared laser energy to receivers on the ground to produce energy, produce hydrogen, produce electrical power, produce heating. We can also put satellites in space to collect sunlight to beam energy to propulsion systems. So here's a space-based propulsion laser. And basically what happens is it flies overhead, and because it can dynamically allocate its laser beams using a holographic technique, it doesn't have to be in a stationary orbit, and the receivers don't have to be stationary. And this is the secret of Star Wars, of the Strategic Defense Initiative. Satellites could fly overhead and target things and destroy them. Well, this is not a destructive beam. It's a power beam. It's powerful enough to energize a rocket, but it's not powerful enough to vaporize the rocket. So there's a fine line there between destruction and production. So basically, we have a space-based propulsion laser in orbit around the Earth that communicates with receivers on the ground or in flight. And millions of beams are produced simultaneously for millions of receivers. And these are vehicles like this Audi Calamaro, a flying vehicle that has a propulsive skin, millions of rocket elements coating its surface, receiving laser energy from space, infrared laser energy from space, and able to fly. So we have MEMS-based propulsive skin, solar powered from space. Flight times for these things are measured in minutes. We can go from anywhere on Earth to anywhere else on Earth in 40 minutes. We can fly at any altitude, any range. It's silent, safe, reliable, automatic, instant transport, anywhere, anytime, with zero emissions at very low cost. This is the transportation mechanism of the future. This is where we need to be. We'll go into each of these. Silent. Well, each rocket is smaller than the diameter of a human hair. And so each rocket is very quiet. And they can operate in conjunction with one another to maintain that silence. Safe, if one rocket blows up, it's not a major event. It basically ceases to operate. Reliable. There are millions and millions of rockets. The odds of more than 1,000 being destroyed at any one flight cycle is astronomically low. The odds that the thing won't operate is zero. It will always operate, and we can always monitor its degradation of performance over time and replace it after a certain number of flights. Here's another Audi concept car. It's called the Shark. It's a flying car. It's a very beautiful vehicle. No wheels. This is the back of it. Here's what it looks like inside. And it basically flies by propulsive skin. Propulsive lasers also have deep space applications. Just need to mention this. This is something that we should also consider a very positive thing. Deep space applications of space-based propulsion lasers can spread across the solar system. With slight change of application from rockets to laser light sails, Bob Forward in 1983 worked out the details of interstellar transport. We basically take a solar pump laser in space, project it through an adequately sized lens, and reflect it off of a very lightweight reflective foil. That lightweight reflective foil will accelerate to very close to the speed of light. The problem was stopping it, not getting a piece of film going that fast. And Bob's idea was to break the film into several parts, and then basically, when you wanted to stop, release the major part of the film and reflect the energy back to the smaller film, slowing it down, while the major part of the film went on its merry way. So with a single laser on Earth, or actually in Earth orbit, or in Sun orbit, you could project a beam, ride it out to a star, and stop there. And you could even return by the same technique. And so we have at our disposal a means to travel to the stars at near the speed of light. Once we're at another star and we build laser beams there, then we can have a much simpler system. But this is a system that is perfectly suitable for exploration and development of star systems. This is a artist's rendering of what the laser light sail would look like as it slows down at Epsilon Eridani, which seems to have Earth-like planets in orbit around it, about 40 light years from Earth or something like that. So we have the technology. We've had the technology for decades to solve all of our transportation problems on Earth. It's really, they're astounding, they're remarkable, they're science fiction-like, but they're also use many aspects of secret technology that's been developed over the years through the Cold War. And this is why they're not in wide use. We need the United States, by changing its approach, by changing its paradigm, by changing its connection to these technologies, can radically transform the nature of transportation in the world and radically benefit by creating trillions of dollars in wealth. It's remarkable to me that Ford and Chevy and Chrysler are going out of business, and we're sitting on this technology in a false belief that we're more secure by not talking about it. It's ridiculous. Okay, so now that I've convinced you, hopefully, that we have the technical means to do whatever the hell we want in the world, what are our goals? These, I think, are achievable goals for the United States to lead the world into. And they're goals that provide greater security for the United States than the United States enjoys at present. And there are goals that provide continuing wealth for the citizens of the United States and of the world. Our goal should be to have 8 billion people living in the year 2040, creating $1 quadrillion a year. At present, in 2010, the Earth's population generates $70 trillion a year. Out of 3.1 billion workers in the world, there are a billion unemployed, there are another billion that are underemployed, and there are another billion on top of that that could be better employed. So, there's a lot of opportunity there for growth. So, what we're talking about is going from 70 trillion per year in 2010 to $1,000 trillion, or $1 quadrillion a year in 2040. That's a growth rate of 9.25% per year. Can we do it? Can we sustain global growth on that scale? And that's a good question. Many people say no way. And I would say, look at where we're spending our money. I had mentioned that all the things that I spoke of earlier are in some way connected to classified programs, connected to concerns about proliferation of missiles or nuclear technology or laser technology. And so they're not in wide use. They're not even credible in many people's minds. But they are things we know how to do. And so without this knowledge of our capabilities, an ignorant person would say there's no way. And I would say, in addition to our way of thinking about these technologies, let's look at what we're spending our money on. Worldwide, the world spends $1.7 trillion a year on warfare. In the 20th century alone, over 200 million people died in war. We spend less than $50 billion a year, $0.05 trillion, in forming capital for new businesses to create jobs and wealth for people. If we have this approach where we are blind to our capacity as a technical species, and we do not question what we are spending on war, and we do not demand that we spend more on humans, beings, on their productivity, then yeah, there's no way we're going to survive. There's no way that we can get better. But if we take a reasoned approach, if we, like Switzerland, develop a mutual defense agreement among all nations and fund it at about 10% the level we fund war now, we would not have problems with warfare. We would not have problems with international crime. We would not have many of the problems that we face today. If we took that savings and made it available for capital formation and made the technology available to qualified users along with this capital, we would find there would be a multiplicative effect with private capital coming to bear, and we would have more than enough money to do major transformations of life on this planet along the lines we just described. The Earth would be a global residential park. There would be no industry, no farms, no forests on the Earth. There would be just basically a nature preserve, and in that nature preserve would exist people. How many people could be supported from space on Earth? Well, Chile is equal to about 6 Californias. Have you ever been to Chile? It's on the Pacific coast. It reminds you of California back in the 40s and 50s. Very few people live there. Beautiful place. Mountainous. It's about equal to 6 California. Indonesia has got 3 main islands, but it's got 16,000 smaller islands. It's equivalent to about 16,000 Hawaiis. Australia is equal to about 25 Arizonas in the center and 17 Californias on the coast. So again, beautiful country, a beautiful coastal region, fabulous interior. Again, California is a great place to live. Hawaii is a great place to live. Arizona is a wonderful place to live. Just these 3 countries alone could absorb over 20 billion people. If you just take the population of California, Hawaii, and Arizona and then multiply those populations by the numbers here, you end up with 210 million people living in Chile, 20 billion people living in Indonesia. And again, they're not crowded. As a residential park, as a residential area that imports things and recycles things and lives lightly on the land, Indonesia would not be overpopulated any more than Hawaii is overpopulated. I mean, if you've ever been to Kauai or any of the other islands, they're beautiful places. And people live quite well. There's 1.5 million people that live in Hawaii. Well, if you have something that's 16,000 times the coastline and area of Hawaii, you can have 16,000 times the people. So the thing is that, not that we would put that many people there, but the thing is that the Earth could easily support 8 billion people with appropriate industrial infrastructure on orbit. This is what we're talking about, getting to that point. So you have a global residential park, $125,000 per person per year, 1 quadrillion people, $1 quadrillion divided by 8 billion people is $1/8 per person per year. That means a family of 4 makes $10,000 a week. And using the technical approaches that we're talking about here, their environmental impact today is 1/20th of what the human race today has on the Earth. There's no CO2 production. There's no farming on Earth. Very little. There's very little forestry on Earth. Very little mining on Earth. It's all done in space. The only thing done on Earth is recycling. So this is what we're talking about: a global residential park on Earth and a space-based industry to support it. We separate our industry from our biosphere to create the type of future that we want and the type of future that we deserve. So to recap, our space-based industry starts with communications. We use global broadband to implement a form of telepresence in addition to existing internet protocol. Energy. We cut CO2 emissions by 2040 to 10% of today's, and hydrogen provides 20% of the total energy of that era, but there's a period of time in which it provides nearly all our energy. Then it's augmented by space-based laser, which provides 75%. Raw materials. We use our energy to recycle, and we use existing carbon sources and existing ceramic clay sources with that energy to radically reduce our use of materials and make things less intense. We use the ocean as a source of rare metals and rare earths, and we use space-based metals and rare earths ultimately to reduce our impact on the oceans. For food, we use energy again to recycle. We use high-intensity greenhouses. We use telerobotics to make efficient use of labor. We use off-world farms and forests and off-world processing to further reduce impact. And for transport, we use aerial transport using MEMS-based propulsive skins, no roads. We augment transport with telepresence so that travel is minimized, and the whole sky is available to our transport mechanism. We use accurate GPS-guided systems that are highly automated, totally automated, and transport time in minutes. People traveling from point to point on Earth, we'd have billions of vehicles, but only hundreds of millions of vehicles would be in the air at any one time. There's only transport time of a few minutes, and so there's not a whole lot of people in the air at one time, and they're spread over the entire Earth. So even though we're talking about billions and billions of transports a day, we're not talking on a square mile basis. So we're talking about a very rare occurrence that you would even see one of these things outside of a city. And cities would dissolve as well. So basically, we're talking about a sustainable industrial future using high technology. I want to talk next about the reality of 2040. There are two ringers that really make any talk of technology almost a slam dunk winner. One is the technological singularity. By the year 2040, many experts estimate that our computing capability will exceed our biological capability. That is, computers will be smarter than people. That is a great benefit if the computers work on behalf of people. That is, problems we can't solve, we can build a machine to solve for us. Also, many of the things that we do on a large scale will be done on a biological scale by the machines that we make, nanotechnology. So I have not included these. What I have done is just talk about the technologies that we know work, that we know how to make work, and that have been around for decades in the laboratories, unappreciated by business. But the technological singularity will radically improve things. The other thing is possible is a self-replicating machine. This actually is a 3D printer that can print a copy of itself. Um, this is an amazing technology. It's something that, again, was considered in the 50s, and actually John von Neumann built small models that would reproduce themselves back in the 50s, but it has been ignored mostly. But this technology, once it's developed, will mean that will radically transform the way we build things. We only need to make one thing, and if it can reproduce itself, we just let it grow to the number that we need. This is a revolutionary change in our economics and a revolutionary change in the way we do business. This, more than robotics, will reduce labor tremendously on Earth. And it's something that we need to think about, but it also tells us that we really don't have any problems that we can't solve. Really, what limits us is our imagination. Whatever we dream will be our reality. In 1865, Jules Verne wrote Earth to the Moon and talked about a cannon shell being fired to the moon. And that ignited dreams in people. In 1924, Robert Goddard, as a physicist, calculated what it would take to send a rocket to the moon. By 1969, Neil Armstrong landed on the moon. Whatever we dream will be our reality. We dream of life, we will live the life we dream. In 1905, Albert Einstein showed that mass and energy were the same thing. A few months later, Haber showed how that explained radioactivity, and radioactive elements were actually tapping into this mass energy that Einstein talked about. It was only a few decades later that the first atom bombs were built. Here's a photograph of the Ivy Mike H-bomb test, the first H-bomb in the American arsenal, 10 million tons of TNT equivalent. Those tiny specks on the ground there are battleships. Whatever we dream will be our reality. We dream of death, we will die. We see the negative only. That negative will come to dominate our lives and kill us. Here's a artist's rendering of a design, very worked out in great detail, in 1929 by John D. Bernal. It's a space city of about 100,000 people. He dreamed this in 1929. Not only just a dream or a fantasy, he's an engineer and a scientist. He worked out the details. We know how to do these things. Buckminster Fuller developed the geodesic dome. He showed in 1962 that if we build the dome a certain size and warm the interior by a few degrees, it will float and carry tens of thousands, hundreds of thousands of people by hot air balloon anywhere on the world. This is a fantastic concept. It's a concept that would radically transform our approach to property, nation states, and any number of things. It's something that we've barely even considered, but it's something that technologically could be done very, very easily. Whatever we dream will be our reality. We dream of life. We can live the things we dream. In 1978, Gerard O'Neill designed a space colony. Basically, Gerard O'Neill designed pressure vessels for particle accelerators for CERN and Fermilab. These things were miles in extent. The vacuum chambers, miles in extent. He realized that if you're surrounded by a vacuum, you could make large pressure vessels the same way. We already build these today. We know how to build large pressure vessels. We put large pressure vessel in orbit and spin it. We have a colony, not just a city. We have an entire state that we can make on demand. And by moving asteroids around and bringing it close to enough for teleoperated robots, we can do this. We can build these things. Whatever we dream will be our reality. So what we choose today determines the quality of our life tomorrow. All I'm saying in this lecture is that we have the means to choose wisely. We are not forced to any negative consequence because of resources or limitations of any sort. We have the technical means and have had the technical means for the last 60 years to do whatever we want on Earth and in the solar system and beyond.